Oh, yeah.
All right, good morning, everyone. Berkeley time has elapsed, so let's go ahead and get started. Hope everyone's doing well today. We are going to be talking about FPGAs, as you can see, but as you hopefully know, you have a midterm coming up next week. And so we're going to take some time to dive back in the archives of your brain and dredge up the stuff from 3 weeks ago or a couple of months ago and do some midterm review. Okay, so let's get started with this warm-up. Please go ahead and try this on your own for a couple of minutes. All right, how did we do? So Tuesday's lecture on logical effort and sizing complex gates or figuring out the delay through complex gates, that's not in scope for the midterm. But you do need to know how to size the gates, as in this example here. So this idea of sizing a gate to match a unit inverter, figuring out what the transistors need to be set to sort of intrinsically for the topology of that gate is something pretty fundamental to understanding gate sizing in digital circuit design. Yes, question before we go over the answer.
Non-integer size.
You can use non-integer sizes, yeah. In a FinFET process, that's actually problematic, but let's hand wave that away for now. One of the nice things about gate all around is that it actually lets us once again go back to arbitrarily sized transistor widths rather than being restricted to an integer number of fins as we are in FinFET process. So yeah, let's abstract that away. We'll live up at this level of abstraction here. We're not going to worry about what's going on too much under the hood with the physical details of how these transistors are constructed. So let's start with the NMOS, the pull down network. How's that sound? If you look at the NMOS network, it's sort of in three parts, right? It has kind of E hanging out at the top here, and then it has this A and B parallel part, and then the C and D parallel part. So these three parts are in, if I just take each of these three parts, think of them as one segment. Those parts are in parallel or in series. That's right. These are in series. And does series increase or decrease resistance? Right. Resistors in series increase resistance. And so in order to overcome the higher resistance, we have to make these transistors stronger or weaker. Another way of asking that is, do we need to increase or decrease the width compared to the unit? Increase, yeah. When we talk about a strong transistor, that's a wider transistor. It has lower resistance and it can drive more current. Okay, you'll hear this concept of stronger drive or weaker drive is a common simplification to think about this. So we have three in series, and so each of them needs to be 3 times as strong, right? In order to match the drive of the inverter. It's a common shorthand to just write the transistor widths inside the transistor like this as a shortcut for how we diagram the sizing inside a logic gate. So the answer I've written here is correct. You'll notice that I sized, for example, the A and B transistors the same, and the C and D transistors the same. Can someone explain why all of those transistors are 3? It seems like these are in parallel, so maybe that should affect the sizing. Yes.
We only care about the individual paths. So each path that you can get to the output through the NMOS goes through 3 of the transistors. So there have to each be a third the resistance, for example.
That's right. Yeah. So the response was we only care about the individual paths. Another way of thinking about it is we always need to size for the worst case. So in the worst case, this network's pulling down, but maybe A and D are off, and we're only pulling down through B and C. And so we need to size the B and C transistors to size 3 so that the resistance sums to 1, right? Yeah.
So if we see a question like this in the exam, will we have to find the most efficient combination of sizes that makes it work, or just a combination of sizes that makes it work?
This is the only set of sizes that matches the resistance of a unit inverter for the NMOS, right?
So the bottom or at about 2.7 and the E one a little bit bigger, it's more efficient. Yeah.
Okay. I see what you're getting at. Yeah, you can with one additional level of detail, you can try to play some tricks to size the different stages in the network differently. The trouble with that is we don't necessarily know which signal is going to be turning on first and which one's going to be turning on last, right? So certainly for the level of abstraction that we're using in this class, I would recommend just sizing them all equally. Okay, so that was NMOS. Let's talk about PMOS. PMOS has 3 paths in parallel, right? But we basically just said parallel doesn't really count for sizing because we can only guarantee that one of those paths is going to be on at any given time. So can someone give their answer, how they sized the transistors in the PMOS, the pull-up network? Yes. Mm-hmm. Mm-hmm. Looks good to me. Any questions about it? Right, if E is on, that's just the same number of transistors as in the unit inverter. But if A and B or C and D are on, that's twice as many transistors. And so we need to double the width in order to match the resistance and match the current. So this is how we size a complex gate. You can apply this technique to sort of gates of arbitrary complexity. In practice, for reasons I think that we won't go into detail about in this class, but in practice, it's very rare to have gates that have more than 3 transistors stacked in series like this. So it would be very rare in a real technology library to have gates that are much larger than the one we're looking at here. Okay, and for the bonus question, you would need to have kind of filter back into your brain about Boolean logic, sum of products form. Recall, of course, that you can do this either from the PMOS or the NMOS network. Doing it from the PMOS in this case, I think is a little more convenient because it just winds up in sum of products form sort of naturally. All right, so recall that for the PMOS, when the input is negated, right, then it's pulling that output up to 1. And so if we have A negated and B negated, then the output is 1. Or C negated and D negated, or E negated. Right, that's just reading directly off of the pull-up network there. If you like, you can also do it from the NMOS, and then you need to do some Boolean manipulation to put it into sum of products form. You should get the same answer either way. Okay. Feeling all right? Starting to turn those brains on a little bit this morning. How are folks feeling about the midterm on Tuesday? Can I see a quick fist of 5? 5 is, it's going to be easy peasy. 3 is, I'm pretty sure I need to study quite a bit. 0 is, oh man, I don't know. Okay, well, I'm seeing a wide range. So we will spend a little more time. I will orient a little more time during class today to focus on midterm review. Hopefully that'll start to jog your mind about at least some of the topics that you need to go study on your own. I also encourage folks, if you haven't attended discussion this week yet, go to tomorrow's discussion section. If you can make it, it's all midterm review. And then feel free to stop by office hour. Prof. Shao, as I mentioned at the start, is out of town this week and next week. So she will not have office hours today or next Thursday. But my office hours are still on next Tuesday. And then, of course, staff are available to help out, check the course calendar for details. Okay, so let's briefly recap last lecture where we talked about logical effort. Once again, logical effort is not in scope for the midterm. So we're only going to talk about this very briefly today, and then we're going to kind of put it on the shelf for a couple of weeks. Logical effort is a really elegant concept in digital circuit design, right? We started with these very complicated transistor models, 3 different operating regions. They have these complex exponential relationships between how the voltages between the different terminals affect the currents. There's a lot going on there, right? And by the end of the last lecture, Prof. Shao showed that all of that complexity can be approximated pretty well and abstracted behind this simple concept of logical effort, which says that gates, based on their topology, have an intrinsic drive strength. There's an intrinsic factor in which they're worse than driving the next stage compared to an inverter. And it only depends on the topology itself. And so for any gate type, like a NAND or a NOR or an XOR, we can do the logical effort calculation and then use that for every NAND or NOR or XOR going forward. And we showed the steps to calculate logical effort and the parasitic factor P, right? We size the transistors so that R matches the unit inverter as we just did in the example. And then we calculate the ratio of the capacitances to find LE and P. And then toward the end of the lecture, we showed how we could use logical effort to analyze arbitrary multi-stage paths of complex gates. Okay. And that's, but when you run in ASIC lab, when you run synthesis and it gives you a timing report and reports the delay of a path, it's doing a version of that analysis effectively, right? Where it's figuring out, okay, for this gate sizing, what is the delay? And therefore, in the synthesis optimization loop, how should I size the gates? Right? There's a lot more details going on under the hood, but at a high level, it's similar to what we did in lecture. Okay, any quick questions about logical effort? Yes. Say again? Yeah, so at the end of last lecture, we went through a gate sizing exercise like is done in the synthesis tool. I don't want to spend more time on that today because again, it's not going to be covered on the midterm. So let's put it on the shelf. We'll pick up on that in a couple of weeks, and we will review it and do some more examples before moving on with new content. Okay. All right. Today we're gonna have a little brain snack. This also topic will not be on the midterm, but it's cool to learn about. Topic is FPGAs. So who's in FPGA lab? Okay, be nice. So this lecture is for you all FPGA lab folks. Okay, it's all eyes on you. Okay, you finally get to figure out what's been going on under the hood when you're pushing the button and, you know, it's running synth, running impl. Like, what is it actually doing? How is it actually taking your RTL and turning it into hardware? We're going to see that today. Okay. This is cool to know about, even if you're not an FPGA lab, because FPGAs are used pretty widely in industry in various places. And so it's good to understand the basics of how they work. And we'll sprinkle in some midterm questions in the middle. So FPGAs are, oh gosh, what is that? About 40 years old at this point, the concept for them. So not as old as ASICs, right? ASICs were chugging along already, integrated circuits in the early 80s. But back then, right, you were probably in a 0.5 micron process or a 1 micron process. Right, so that's 500 nanometers compared to 3 nanometers today. So you got very few transistors to play with. Every transistor was sacred. You wanted to make sure it was doing exactly what you needed it to do to make your processor a little faster or whatever function you wanted. And so this guy, Ross Freeman, had this radical idea that instead of every transistor is sacred, let's put down a uniform grid of these programmable logic blocks that can be connected in a configurable way. They can be reconfigured with software. They can be reprogrammed in the fields. We'll call it a field programmable gate array, right? Now, in the 80s, this was heresy, right? Because this means that for some applications, you're going to have half of these programmable gate arrays that are just unused, sitting there doing nothing, while the rest of them are being used for your function. And then maybe you reprogram it and, well, these ones are used, and now these ones are sitting there. Okay, this really cut against the grain of every transistor being sacred. But one of the magic sources of innovation in this field is that Moore's law for a long time let everyone see where the puck was going, right? You knew where the future was going to be in 10 years and 20 years because of this insight of transistor scaling. And so Ross Freeman said, yeah, this seems like kind of a silly idea now, but going forward, eventually we're going to have so many transistors we don't know what to do with them. And so this is actually not as big a deal as people think. And so that was the genesis of the first FPGA, which is shown here. And he went and founded this startup called Xilinx with some of his buddies to pursue this idea. And so FPGAs have many similarities to ASICs in how you design for them, but they have some key differences which make them really cool, right? Instead of having to do a tape out, which takes 3 months and is extremely expensive, you can tape out a new design every few minutes or hours, right? You push the tools, it generates a bit stream, you program it, and you've effectively taped out a new block of hardware. They're reprogrammable or reconfigurable. Obviously, this is a huge advantage compared to ASIC, where once you've taped out, that's it, you're done. You need a new function, too bad. You had a bug, oh, that's no good. You're in trouble, right? FPGAs take a lot of the pressure off of all that stuff. The disadvantage of FPGAs is that in order to get that programmability, you're worse on the magic metrics, right? PPA, power performance area. So FPGAs are not as efficient as ASICs for any given task that they've been programmed for. So it's a trade-off. And then modern FPGAs have taken that basic concept and added lots more bells and whistles. And we'll talk a bit about all the extra goodies that you can find on a modern FPGA beyond just this kind of sea of programmable blocks. And so the theory is kind of shown in this plot here, where the big advantage of FPGAs is that they have much lower NRE, non-recoverable engineering effort, right? So your total cost, recall all the way back to lecture 2, your total cost is NRE, non-recoverable effort, plus unit cost times number of units, right? And so in general, for ASIC, the more units you're building, the more the ASIC is going to win on cost, right? Because the unit cost is less. This slope is less of this line. But for FPGA, the NRE is low. And so therefore, the y-axis is low. And so even though the slope is higher, right? If you're in this range, then FPGA is going to win on cost. And furthermore, process scaling says that ASIC NRE is going to keep going up over time. And so therefore, the theory was that this crossover point should shift. So each generation, FPGAs will become more and more advantageous over ASICs, right? Yes?
Approximately, like how many units would it take for the crossover?
Super good question. And I don't think I'm able to give you a generic answer to that because cost depends on a tremendous number of factors. I would say order of like 100,000 to 10 million would be something like a modern crossover point. But we'll talk later about some of the other trade-offs here and when people actually decide to use FPGAs versus ASICs in practice in industry today. So as you probably know, there are 2 dominant FPGA makers. Xilinx makes the boards that you're using or makes the chips you're using in your lab. They were acquired by AMD some years ago. Altera is the other big player. They were acquired by Intel even before that, but now they've been de-acquired last year. So now they're back to being a standalone company again, although I think Intel still has like 49% stake. They have some weird relationship. Intel's a mess. Anyway, so these are the 2 dominant FPGA makers. There are a bunch of startups or smaller players in the field as well, but these are the most common ones. And so there's this sort of conceptual plot that people like to draw where there's a trade-off between flexibility on one axis and performance on the other axis. And so the highest performance, but the least flexibility is your ASIC, right? Because you tape it out once and it can only do that. The most flexible thing is a CPU, right? It's Turing complete. It can run whatever code you like. But CPUs are not very performant compared to an ASIC or compared to specialized hardware. So GPUs were one attempt to address that. by making CPUs into these massively parallel machines that are faster but harder to program. FPGAs are kind of coming at that gap from the other direction. They're saying, let's take an ASIC, but make it reconfigurable. We'll sacrifice some performance, but make it more flexible. Okay, so there's this whole sort of design space. And depending on your application, you might land up in a different one of these bubbles. So let's start to talk about what's inside an FPGA. The basic idea is quite simple, right? There's just this two-dimensional array of logical blocks. They have flip-flops inside them. They have some combinational logic inside them. They're shown in these green boxes in the diagram here. And the function of each of these logical blocks is configurable, programmable. And so the user can configure the function of each block as well as how the blocks are connected to one another. And that's it. That's the basic idea. We'll talk more in a moment about the details of what's inside these. But at a basic level, it's just this sea of programmable fabric and programmable interconnect. So the logic is called combinational logic blocks, CLBs. This is the fundamental building block of FPGAs. And then you have these interconnects, these switch boxes, these switch networks that are wires that can be connected or not connected at any intersection. And that allows the blocks to arbitrary blocks to talk to one another. So that at a high level, that's what's inside an FPGA. Any high level questions so far? Yes.
What makes FPGA less flexible than GPU? Because can't you I guess program for CPU and GPU in your FPGA, or is it about the limitation of your number of ones?
Yeah, so the axes here are very conceptual or fuzzy, right? So I think at various times people have tried to make arguments about this bubble should really be over here, or this bubble should really be up here. People try to tweak their architectures to move around on this plot. I think the big difference between FPGA and GPU in terms of flexibility is if you want to run, if you want to do two different things on a GPU, it's just a matter of launching a different software binary, which you can do in seconds or milliseconds. Whereas if you want to have different functionality running on the FPGA, you have to flash a new bit stream on there, which is slow and sort of takes kind of specialized hardware. So I think for that reason, people would generally think of FPGAs as less flexible than GPU, as less flexible than GPUs, just because they can really only do one. The common use case for FPGA is you do one thing at a time for a long time. You don't reprogram them that often, order of, hours to days if you're debugging some hardware or something, or even order of months to years if the FPGA is just sitting in a server box somewhere and very occasionally you need to update the firmware or update the functionality. Yeah, that's a great question. Okay, so you'll see if you are an FPGA nerd, I guess, and you go looking in the data sheets, you'll see these giant tables like these that talk about what's inside FPGAs. And so these Vertex Ultra Scale, these are kind of the biggest ones that you can get your hands on these days. Along the different columns are just showing different variants, different models of the FPGA. And then the rows are kind of showing the different components and sort of how capable each FPGA is. So you'll notice one thing that we've talked about already, CLB, these combinational logic blocks, right? You'll notice that's in thousands, right? So the largest one on here has 1.7 million combinational logic blocks, right? Which is a lot. Oh, yeah, you're right. This one has 4 million combinational logic blocks. Anyway, there's all these other statistics here. It can be a little overwhelming, but my hope is by the end of the lecture today, you'll feel a little more comfortable reading these tables and understanding more of what these different rows in the table mean. Okay, time for a break. By break, I mean midterm review, so not a real break, I guess. But please go ahead and try this problem on your own. Take a look at it. A couple minutes, I'll open up the poll. All right, the poll is now live. So if you have been able to figure out the answer, please go ahead. Head to the Poll EV website. Since we haven't used this in a couple of weeks, so you'll have to drag it out of your browser history and then respond to the poll. Okay, let's take 30 more seconds on this one. Okay, so we've only got about half responses on this one. So please, if you haven't already, please go ahead and turn to your neighbor and try to convince them that the answer you got is the right answer. Go ahead, find a neighbor.
Practice, drop, cover, and hold on.
All right, let's come back together. Let's bring our attention back up here. So one of the things that I think is a little confusing about understanding the physical dimensions of transistor behavior is just that we can only draw two-dimensional pictures of the transistors. So we can draw it kind of from the top view or from the side view, but it's if you don't have in your brain like how a transistor physically looks, it can be a little hard to build intuition around this stuff. So I borrowed some of my son's Duplos to try and illustrate what a transistor looks like. It's Legos for little kids. So this is our transistor, okay? This is the source, this is the drain, this is the gate. So the channel, I guess, would be under here, right? So remember, when we talk about resistance, we're talking about the resistance of this channel when it's turned on by the gate, right? And so it's the gate size determines how much channel there is for current to flow, okay? So most of the time when we talk about transistor sizing, right, we talk about increasing the width. So a wider transistor, not there. A wider transistor is like this, right? So the distance here is the same, but we've doubled the width. Does that make sense? Okay, a longer transistor is like this. So the width is the same, but now we've made it longer. Okay. So let's think about what that does to resistance and to capacitance. Okay. Capacitance is just the area of this guy, right? Because this is the gate. This is what the previous stage is seeing. This is the capacitance between the gate and the channel. There's a little very, very thin, angstrom level thin layer of oxide here between them. So how much gate there is the capacitance. So when we doubled the length like this, did capacitance go up or down? That's right, yeah. And in fact, increasing width and length both increase the capacitance. What about resistance in this case? Yeah, so when we increase length, resistance is also going up, right? Because you think about the electrons, they used to just have to go this far to get from source to drain. Now they have to go this far through the channel. And so the resistance, you know, how difficult it is for electrons to move, or holes to move, if you like, is increased. And so if R and C increase, we know that delay, we have detailed equations, but we know that both of those are going to make delay worse, right? They're going to make delay slower. And so most folks correctly stated that increasing length will increase delay. And so for that reason, we almost always size our gates with minimum length transistors. And in fact, we almost often don't think about length as a possible sizing parameter, right? We just think about minimum length to make it as short as possible here. And then if we need it stronger, we make it wider. Occasionally, we will build transistors that are minimum width and greater than minimum length, which makes them really slow and crummy. But it turns out that there are certain cases where we actually want slower delay. We haven't talked about those cases yet, but it'll come up later. So just keep in mind that length is also a sizing parameter in our transistor model. So this was more of a conceptual question. You didn't in the end need to work out any equations to sort out this. It would also be good to understand the equations and the math, how much does the delay decrease? But the first and most important thing is to build up a conceptual understanding of, well, if this changes in this direction, width changes wider or narrower, what's that going to do? If length changes wider or narrower, what's that going to do? Any questions about it? All right. Put my Legos away. So let's talk a little bit more about FPGAs. And in particular, we're going to dive into these combinational logic blocks. What are they made of? What makes them tick? They're actually pretty simple, the insides, as we'll see. This is a very basic version of what's inside a combinational logic block, a CLB. So it has something called a lookup table, or LUT, for LUT in this case, because it has 4 inputs, 1, 2, 3, 4. That's going to do our combinational logic. It has a flip-flop. That's exactly the same as the flip-flop that you would see in an ASIC. And then it has, we're going to see more of these. It has a mux, a multiplexer. These are actually traditionally drawn in this shape. Right? This is a typical hardware diagram for a mux. So this mux is just saying you can either use the flip-flop or skip it, right? And then there's this SRAM, which we won't talk about more today, but basically there's some state that configures the mux. It tells us whether it should be set to 1 or 0 for any particular programmed configuration of the FPGA. So the most mysterious thing out of everything I just said is this for LUT, this lookup table. And so we're going to talk in detail about how to make that. A lookup table turns out to be very simple. It's just a big mux. So this for LUT is in fact a 16-to-1 mux instead of a 2-to-1, like we saw on the previous slide, but it's the same concept. It has 4 inputs, and then it selects. It has 4 select signals, select bits, and then it's selecting between 16 possible inputs and passing one of them to the output, right? And so in particular, an n-bit LUT is implemented as 2 to the n 1-bit memory, right? These memories here are denoted as latches. For our purposes today, you can just think of latch as the same as a flip-flop or a register, right? It's just something that stores state. So for this for LUT, we're storing 16 bits of state in the latch. And then the inputs just select between them. Should I pick bit 0, bit 1, bit 2, and so on. And so as we'll see in a moment, this n-LUT, or for LUT in this example, but n-LUT in the general case, can implement any function of n inputs. And so this encapsulates all of the combinational logic that we might want to put on an FPGA. Okay, so FPGAs don't have NAND gates or NOR gates or XOR gates. All the combinational logic is in these LUTs. Okay, let's do a quick example to see how this works, how you would program a LUT for a particular function. Okay, let's say we wanted to, I don't know, program a function like this. Let's say it was A, B, C plus A bar, B bar, C bar. This is a valid combinational function. I'm confident that you all could, if asked, say in an exam setting, translate this into logic gates, NANDs and NORs and so forth. But in an FPGA context, we are not going to map it to logic gates. We're going to map it onto this LUT. So the first thing we need to do is map our inputs onto the 4 select bits of the mux, so the 4 inputs to the LUT, right? So let's just do the mapping in order like this. A, B, C. I guess we have a 4th input that's unused. We'll call that D, but it's not going to matter what D is, for the purposes of our logic function. And then for any combination of inputs, we can write the output. Right? This is exactly the truth table, right, of this function. And so in particular, let's see, we said A, B, and C are all high. We need the output to be 1. So that's these 2 cases down here. And then if A, B, and C are all low, we want the output to be 1. So that's these 2 cases up here. And then for any other combination, it doesn't give out equals 1 in our sum of products form. So we'll set all of those outputs to 0. I'm actually not going to write out all the zeros, but you can fill them in. And so then we just take these 16 bits and store them into the little 16 latches that we have, right? So the first latch will get this one, the second latch will get this one, the third latch will get this 0, and so on. And so that's how we've programmed the lookup table. You can see how as A, B, and C and D come in, we're doing a lookup into these 16 elements, into these 16 bits, and say, well, please take this bit because these are my inputs, right? That's why it's called a lookup table. So hopefully, I haven't proven this, but hopefully you can at least have some idea of how this for LUT can implement any combinational logic with 4 inputs and 1 output, right? Because we can set the values of this truth table to arbitrary 0s or 1s in the latches. So that's kind of neat. We don't need to lower it into gates. We just program this lookup table. Unfortunately, the lookup table size, as you may have noticed, grows exponentially with the number of inputs, right? So for 4 inputs, we needed 16 latches, 16 state elements to store the possible outputs. If you wanted to have, for some insane reason, a 64 input lookup table, you would need this very large number of bits of storage. That's too big. That's not an efficient way to do things. So typically, lookup tables on FPGAs will be restricted to these relatively small values for 4 to 8 inputs. How are we doing, Pen? I'm in trouble. Oh, well. Okay, any questions about lookup tables or how we can translate logic into programming a lookup table? Yeah, good question. Let's talk about that in 1 second. So each CLB combinational logic block contains 2 slices. So we've moved on from like general case to like specifically what is in your FPGA sitting on your lab bench. And we're going to talk about that for the next few slides. So the Xilinx 7 series has 2 slices. Each slice has 4 lookup tables and 8 flip-flops. there are two flavors of slices. So there's the slice M, which is a full slice. It has some extra goodies. And then there's the slice L, which is a little more lightweight. So the advantage of having the lightweight one is you can fit more of them on the FPGA. So the assumption is that you're not going to need all of the functions in the slice M all of the time. And so we'll have a mix of slice M and slice L. And we'll talk about in more detail what's inside them. Okay, so back to your question, here's a lookup table. Your FPGAs actually use LUT5s as the basic building block. Okay, so it's going to have 5 inputs and 32 state elements. You notice that unlike for ASIC CMOS logic, the timing is independent of the function here, right? For in ASIC world and in CMOS gates, if your logic you want is out equals not A, then you just need an inverter. It's very fast, right? Whereas in an FPGA, out equals not A still maps into this 5 LUT. And it takes exactly as long to go through that path as for any other complex function of 5 inputs. So it's sort of, you can see why lookup tables start to get slower in many cases than CMOS gates. But it also makes the analysis easier because whatever's mapped onto them, the timing is going to be the same through it. We program the latches through the configuration. Okay, how do we make even bigger LUTs? Well, we're going to just start having 2 LUTs and muxing between them. So in this example, we have 2 LUT5s, right? But then we have 6 inputs, 5 of which are inputs to the LUT5s, and then one of them is the select signal of the mux that says which one should I be using. And so you can construct a LUT6 out of 2 LUT5s. You could also just make one giant LUT6, but this gives more configurability because you can either use it as one giant LUT6 or you can use it as 2 LUT5s. So this is how the FPGA builds up more and more complicated combinational logic functions. And so this is the very basic view of what's in a slice, right? So it's just these LUT6s, which again have 2 LUT5s in them. There's 4 of those, and then each of them has an optional flip-flop after them. So we'll do a bunch of combinational logic, and then we can either flop it, or we can just go straight out to another slice and do some more combinational logic. Okay, and then the vertex slices add some more bells and whistles. So, well, what if we want to do 7 inputs? Let's give that option. We'll add some more muxes. We'll add some more inputs, and now we can handle a 7-input combinational function mapped into this slice. What about 8 inputs? We can do the same thing. We're just going to add some more muxes and mux between those 2 7 LUTs and give the option of being able to select between all these different modes, right? So now, one second. Now we can have a single 8-input lookup table, or we can program it as 2 4-input lookup tables, or I'm sorry, 2 7-input lookup tables, or 4 6-input lookup tables, or 8 5-input lookup tables, right? The name of the game here is configurability. They're trying to build the FPGAs in the way that there's maximum flexibility to program different logic functions into these blocks. Okay, yes, question?
The 6, 7, and 8 actually physically hardwired.
Yeah, so everything I'm showing here is physically hardwired. All of these muxes and lookup tables are physically what has been taped out in the FPGA that's sitting on your bench, yeah. And then the programmability comes from setting all of the values in the lookup tables, setting all of the select bits for the muxes. That's going to set it to the particular function that you've defined in your RTL. Okay, one other specialization. We won't actually talk about this in detail because we haven't talked about arithmetic circuits in detail yet. That's a post-midterm topic. But there's a common case where you're building an adder and you want, rather than doing some combinational logic and having it flow to the output, you actually want it to flow from one lookup table to the next within the same block. And this is called ripple carry addition. And so you can see at a high level, they've added these extra muxes so that data can kind of flow internally through the slice rather than just doing a single computation and then going out of the slice. This is very useful for synthesizing an adder in the FPGA.
Without the special carry chain, right? You just have to use extra routing stuff outside the block.
Right, correct. You could do this with 4 slices, but a lot of the optimizations and why they've designed the FPGA this way is trying to be able to implement more and more logic blocks in fewer number of slices. Yeah, so you're absolutely right. This is an optimization. Okay, so oops. The figure on this slide has disappeared, but it's the same one from the very start. So we put this all together. This is a slice L. I apologize for the missing figure. I'll go ahead and add that in to the online version of the slides. The slice L just consists of all the features we talked about on the previous slides, right? So it has these 5 LUTs that can be reconfigured and muxed up to an 8 LUT. It has the optional flops at the end. It has the specialization for the carry chain for implementing a synthesized adder or something similar to it. And then the slice M's, we're not going to go into detail, but they add even more bells and whistles into the slice with the hope that you can map more and more complex functions onto a single slice. That's the core building block of an FPGA. Any questions about what's inside a CLB, a combinational logic block? Yes, one question.
Start with 5 and then go up to this building.
Yeah, that's a good question. Can anyone think of why we might want to do it that way, of having 5 LUTs that compose the 8 LUT rather than just building one big 8 LUT? Yeah, right. So 8 LUT would need how many state elements? 2 to the 8th, which is big. It's 256. Yeah. But if you build it out of 5 LUTs, you still end up needing the same number of state elements, right? It's just built out of smaller pieces. So it's not actually saving you any state that you need. Yeah. Yeah, exactly. So you can either use it as one big 8 LUT, or you can implement 16 parallel functions as the 5 LUTs, right? Or you could have a 1 7 LUT and 8 5 LUT. You know, you can do it in many different combinations, allowing it to either be used for a lot of little things or one big thing. That's kind of the way that they decided that way. All right. Yeah, I don't know what's going on with my slides here. Let's go out. All right, it's not displaying correctly, but we're gonna take a little break. I've opened up the poll. Let's try presenting again. Yeah, here it comes. Okay, so 2-minute break. Please go ahead and respond. I understand that this has been a point of some amount of heated debate on Ed, that there may be mis or disinformation flying around with regard to certain people's statements. So let's keep it respectful. Let's see how we're doing here. Oh man. This is a very tight race here. I'm very curious about the one undecided voter also. Two undecided voters. Okay. Does anyone want to make an argument other than like that's the lab section I'm in and we're the best about why one is better than the other? Yeah.
Like when I talk to people about it, I just say that like A6 server is actually like our devices. So,
Hmm. Interesting. Any other thoughts? It's a true statement. Like your computer and tablet and stuff are have A6 in them. Yeah.
It's hard to design A6 if you don't have FPGAs sitting around, so you sort of need both.
Interesting. All right. Well, we'll see. We're going to talk a little bit more about the rest of the goodies in FPGAs. We'll see if we can change any minds by the end of the lecture. Now it's just black. Man, PowerPoint is really falling over today. PowerPoint has crashed. I apologize. One moment. Wait, is that it? Oh, geez. Okay. Okay. This should be what you're looking for? All right. Okay, administrative stuff. I don't want to spend too much time on this, but the midterm is next week, next Tuesday, 7 p.m. for most of you. There will be no lecture next Tuesday morning. So I'm saying it loud and clear. Please don't show up here next Tuesday morning. You'll be all by yourself. Very sad. Next Thursday, we will have a guest lecture where we talk a little bit more about FPGAs and their applications. So the speaker is from Apple. He's given this lecture a number of times in the course before, and it's gotten very good reviews. So definitely encourage folks to attend. Homework 6 is due tomorrow. This is your last homework on midterm content. We will release homework 7 tomorrow, but it won't be due for 2 weeks. So we're putting it out there, but don't fret about it. And then, of course, your project 1 checkpoints are due tomorrow. It sounds like, based on the number of checkoffs so far, that the Friday lab sections are going to be quite busy. If you can get checked off before Friday, I would encourage you to try to do that. But otherwise, at least, yeah, don't wait till the last minute. It is, checkpoint 1 is light in terms of the amount of typing that you need to do, but it's very important. Having a bad block diagram can cost you many hours of pain down the road. So I encourage folks to take the time and think carefully about this. Yes. Yes, I believe homework 6 is on topic specifically in scope for the midterm. Yeah, it doesn't have any logical effort problems. Okay, any other administrative questions? Okay, let's talk briefly about some of the other bells and whistles in the FPGA. The other sort of fundamental piece, besides the configurable logic blocks, CLBs, is the interconnect. And in terms of area, interconnect actually ends up taking, in many cases, a majority of the area. So it's actually just a sea of wires with these little blocks sitting every so often in between them. This is very simple, so we're only going to spend one slide on it. It's basically wires going horizontally and vertically, and when they cross over each other, there's a single transistor that can be on or off, also programmed by the bit stream by some state sitting on the FPGA. And the transistor is saying, should there be a connection or should there not be a connection, right? And so you can see in this example here, this switch box has been programmed with a horizontal connection. this switch box has been programmed with sort of a 90-degree turn connection, and so on. And so you just set these transistors and it tells which slices, which combinational logic blocks are connected to one another, the outputs of one going to the inputs to the next. And so you can sort of start to see how you can use this to wire arbitrary CLBs together to have arbitrarily complex logic functions, combinational logic, and then state elements, flip-flops, same as you would have in a gate level ASIC design, onto the FPGA. And I say arbitrary up to some size, right? You can make a bigger and bigger design, and eventually you'll run out of CLBs on the FPGA or run out of some other resource and it won't fit. Unless you've done something wildly off base, that shouldn't be an issue for your work in the labs. But it is an issue in real applications where you have to make sure your designs will fit on an FPGA. Okay, so that's sort of the basics of the programmable fabric in FPGAs. What's happened in the last 20 years or so is that they've started to garner more and more bells and whistles, where basically the FPGA designers were figuring out, oh, these are the common applications that people are running on them. So let's harden those. And by harden, we mean design little blocks of ASIC logic that specifically do certain functions so that you don't have to use up a lot of CLBs to program that function. You can just put it on this specialized hardware. And so in particular, a modern FPGA is made up of many different diverse resources, of which the programmable logic is only one. There's lots of them. We're going to talk about a few of these. You can see this sort of cartoon die photo where they have all these different colors here. So block RAMs are an important one. Those in FPGA know that you don't use SRAMs in the same way that you would in an ASIC implementation. Instead, you use block RAMs, which are basically just SRAMs that have been hardened into the FPGA in a certain configuration. And so typically in the layout, they're kind of striped vertically like this. And so you can route to or from those into the logic fabric. They'll typically have different options for sizes, 2 read and write ports, which is nice. Newer FPGAs have larger block RAMs, which means that you can have one big one, which is more efficient rather than having to compose it out of many little ones. But this is the equivalent of SRAMs in the ASIC world. After the block RAMs, they added these DSP slices. So DSP is digital signal processing. Early on, it became apparent that FPGAs were going to be really good at that because you could, have this configurable hardware that was programmed to do DSP. And so they started laying down these specialized DSP slices that are not configurable to arbitrary logic, but instead can only do certain functions, but they do it much faster and more efficiently than if you mapped those functions onto CLBs. So you'll notice a multiplier here. These Z inverse blocks are basically like tap delays in a FIR filter, for those of you familiar with that world, with the DSP world. And then there's addition, or there's sort of ALU here, different selects between them. We're not going to talk in detail about what every little bell and whistle is doing here. Just know that on FPGAs, there's this specialized hardware for DSPs. And if you're doing these functions, you can map to that hardware, and it's more efficient both in area and in power and in performance if you map onto the specialized hardware than mapping into the C of logic. And so I hope now when you start to look at these tables of FPGA stats, and this is the one that you're using in your labs, I believe, that all of this should now be a little more intelligible to you, right? Here's the number of lookup tables. Here's the number of flip-flops. Those are sitting in the slices. Here's how much block RAM we have. Here's how many DSP slices. This is the peak DSP performance on a particular workload, which is an FIR filter. There's a few other things that we haven't talked about. Notably, your zinc parts are really nice because they actually have embedded ARM cores built into them. I don't think that you're using them in the labs at all, but it's very handy in the field to have a processor already ready to go rather than having to map it out of LUTs. And then there's some other bells and whistles as well. So about 5 years ago, let me just discuss this and then I'll take your question. About 5 years ago, Xilinx started fielding this new line of FPGAs that they called Versal. And in addition to DSP slices with multipliers, they actually added matrix multiplication hardware as well, these AI cores. And so the idea was that, well, maybe people want to use FPGAs for AI, and so we'll add some dedicated hardware for matrix multiplication, and you can use it for that purpose. And so in the end, FPGAs end up modern FPGAs tend to, especially the big ones, are looking a little different than they did back in the original concepts in the 1980s. There will be some part of it that's a field of programmable logic, C of CLBs. But then their big chunks are just these different specialized blocks that you can map onto because they're trying to guess what people's most important workloads are and have specialized hardware to map onto those blocks. Okay, yes, question. Yeah, so block RAM is, I mean, under the hood, they are both made of the same fundamental building block. But block RAM is the name of the SRAMs that are instantiated on the FPGAs. It's called block RAM because it comes in these sort of predefined sizes of blocks. So I guess one difference is that typically with SRAMs, you can generate them to an arbitrary size based on the specific configuration that you need. Whereas with block RAMs, you're restricted to mapping onto the specific sizes that are provided on the FPGA. And if it's too big, then you have wasted space. If it's too small, then you have to compose it out of multiple ones. The details in Verilog of how you actually instantiate them are also different. So that I would refer you to the labs in the two different flavors of lab for the details on that. Okay, yeah, and so they call Versal this ACAP. They're trying to move away from the FPGA branding, and they call it a whole new thing, which is Adaptive Compute Acceleration Platform, where again, there is some still programmable logic, right? It still is fundamentally an FPGA, but there's all these cool little widgets. Here's the ARM cores. Here's the AI engines. Here's DDR memory interface, PCIe, HBM, Ethernet. They've added tons of bells and whistles to try and make it as useful for as many specific use cases as they can. So, and I want to talk briefly about the differences in the tool flow, because how you program them is similar in many ways, but does have some key differences. This is the ASIC design flow. This should be familiar from earlier lectures, and especially familiar for those of you in ASIC lab. You take an RTL design, you simulate it for correctness, and then you map it through synthesis and place and route using some process technology libraries and get a GDS, which is a bunch of rectangles that you can send to TSMC for tape out. So FPGA, the nice thing about FPGAs is that you specify the design very similarly to as an ASICs. It's still RTL, it's still Verilog. There are some different details, right? You need to instantiate these BRAMs, these block RAMs, instead of SRAMs, for example. And if you want to do DSP functions, in an ASIC, you would go and implement the code to do a 32-bit multiply, for example. In an FPGA, you would instantiate one of these DSP blocks, which is IP provided by the FPGA vendor. So the details are different, but at a high level, it's similar. And then instead of a process technology, you have a specific FPGA that you're targeting. RTL simulation looks pretty much the same. You still can use VCS or a commercial tool, but the synthesis and implementation, instead of place and route, we call it implementation, are different. One key difference is that they're generally using a vendor-provided tool rather than a third-party EDA tool from something like Cadence. Another difference is that instead of synthesizing into gates, it's figuring out how to program all the LUTs and all the switch boxes and so forth. So the synthesis step is figuring out, what are the programming of the LUTs needed to implement the functions. And then the implementation step is saying, how do we actually map that onto the physical FPGA resources that we have? Which corner of the FPGA is this function going to go in, and this function, and how are they wired together? And then instead of a GDS, you just get a bit stream, which is just a series of ones and zeros that are setting all the muxes, setting all the latches, setting all the state. So it's similar at the high level. It has some key differences. So what's the conclusion here? Right. The original promise of FPGAs is that every generation they would get better and better than ASICs. I think that largely has not borne out over time. There are a couple of important barriers to FPGA adoption that have prevented them from kind of taking over the world, I would say. One is that, this whole idea of ASICs have really high NRE and FPGAs have very low NRE. I think in practice, that's not true because mask costs, the cost of the physical tape out is one part of NRE, but especially in a modern complex design, the engineering work needed to build the thing is the biggest component of NRE. And in particular, to verify the thing is the biggest component, right? And so you need to code up that RTL and verify it, regardless of whether you're targeting an ASIC or an FPGA. And that, as I think you're coming to appreciate in the labs, is very hard to do, right? Hardware design is hard, and there's no shortcuts around that. And by choosing a hardware design paradigm, the FPGA is sort of, it actually ends up being nearly as costly in terms of paying the engineers as an ASIC, right? In many cases. So there's sort of these sweet spots where FPGA applications make sense. Relatively low volumes, right? Number of units to the left on this plot. Can't care about power that much because they're not power efficient. So it's never going to wind up in your cell phone or in your laptop. The unit cost is going to be relatively high because, again, you haven't taped out a specialized chip. You have to buy a new FPGA every time you want to ship something. Your application needs to require low latency or high performance, but not super low latency or super high performance, because then that's out of bounds for the FPGA and you need to go build an ASIC instead. So you can see how this rules out many use cases. And so it's typically limited to relatively specific applications today. I'd say in terms of, taking over the world, ASICs have taken over the world and FPGAs are used for specific things. But that said, they do have some really important applications. And so you can think about, I won't step through all of these, but you can think about how these applications fit into these criteria that I just mentioned. One unsuccessful application of FPGAs, I'd say, is deep learning. As you saw previously, Xilinx tried to get everyone excited about using FPGAs to do deep learning training or inference. They added all this matrix hardware. Microsoft actually had a big project early on in the DL craze to spin up a massive sea of FPGAs in their data centers instead of GPUs and use that for deep learning. It didn't work out. The project is not live anymore. Fundamentally, it turns out that for most applications, if you want stuff to go fast, it's just way easier to program in CUDA than it is to program in Verilog. And so most people, if they need something to go faster, they will figure out how to run it on a GPU. Okay, so we ran out of time for one more midterm question. I apologize. But just to briefly summarize, FPGAs are widely used for hardware prototyping. We talked about the core building blocks. And that modern FPGAs add on all these extra bells and whistles to try and make them more helpful to folks. And that's all we're going to say about FPGAs for now. Next guest lecture, we'll talk more about how FPGAs are used as a key component of designing ASICs, which is one of their main use cases today. Hey, good luck on the midterm, everyone. I will stick around for a few minutes for questions.
Great.